So, good evening, everybody. This is Oxford Quantum Information speaking. We are here today to listen to a talk by Chiara Marletto on locality of quantum theory and Aharonov-Bohm effect. Yeah, but before starting, I'm sorry, let me say a few words, just like to give an outlook of what we are doing here. So we're on the fourth week of Trinity term, and we already had 3 events. We had a flash talks where young researchers from the University of Oxford, they have been telling us about their research in the field of quantum computing. We also had a journal club where our very own Anthony Thompson, he's probably actually listening to us right now. He told us about, he guided us through the paper of Renata Renner with his news paradox, and people say that that was one of the most clear explanations they've heard. So probably it's definitely worth checking out. And also we had a talk by Professor Aspuro Guzik, who is an expert in quantum variational algorithms and applications of quantum computers to quantum chemistry. And also he's doing a lot of other things, and he advertised a lot of things this week, Wednesday. So probably we have all the recordings on Facebook, and maybe you can check what have happened so far. Later we'll have on the 7th week, I guess, maybe 8th, we'll have a questions and answer sessions by Scott Aronson, who is one of the probably leading people in the computer science part of quantum computing. We'll have a talk by Chris Monroe, who is probably will be one of the people who will build an actual quantum computer on trapped ions. And we'll have one more journal club. Also, on next week, we have a quantum coding workshop where Ben Gaderbeck, he's a second-year DPhil in the Department of Physics. He'll be teaching people how to use IBM Python package Qiskit to code real quantum computers. So please check the description on our page and join if you want to learn how to code quantum computers. And in general, like if you have any questions, proposals, anything, just reach us. Reach us, send us a message, any talks, because like my problem was when I got interested in quantum computing, I had anybody around to talk to, and our society, in my opinion, is not so bad opportunity to get acquainted with the people who are sharing the same ideals and the same passion. Yes, and now probably to the talk. So unfortunately, I have been studying telecommunications during my undergrads, and I didn't have cool courses on quantum field theory or general relativity. And that's why I admire theoretical physicists so much. That's why I'm so glad that Chiara Marletto is giving us a talk today. And a few formal words is that she has obtained, like, you know, like on all these talks, some big guys, some chairs, they say, all right, I can say, no, you don't want to. Okay, yeah, they say like these words that Chiara has obtained her bachelor and master degree in physical engineering from the Politecnico di Torino, or if it's pronounced correct. Yeah. Also, she has her DPhil in mathematics from the Mathematical Institute of Oxford, and her research interests include quantum theory of computation, foundations of physics, condensed matter physics, and quantum biology. That's what the Wilson College website says. But what thrills me the most is that she has been working with David Deutsch on constructor theory, or I don't know, probably it's better to say that David Deutsch was working with Chiara Marletto on constructor theory. And as far as I get it, constructor theory is some possible replacement for quantum mechanics, which can be more fundamental than the quantum theory. I may be wrong. Okay, all right. So if I correctly. And so if you ever wanted to listen to a talk of a person who is on the forefront of modern physics, then you couldn't find better opportunity than today. So Chiara, yeah.
Great. Thank you so much for this introduction. This was very nice. And I'm very happy also to see that the society is doing so well. It's, I think it's really exciting that all of these things are going on. And I thought I'd talk about something that is, of course, very controversial, and also touches a bit on a number of things that I think quantum information has clarified a lot for us. So I think it will, I thought this would be nice for the Quantum Information Society to hear about. I would like to share my screen so you guys can see. I prepared some slides, so maybe I can go into that mode. But it says that the host has disabled share.
Have I?
Yes, that's what it says.
Oh, really? I'm sorry. So
no, don't worry, don't worry. I can also.
Have I disabled it? You can't share the screen.
Yeah, that's what it says here.
Oh Lord. Maybe if anybody knows how to fix this in Zoom, please write us a message to a chat or to question and answer, because I can't really. It's a. So I'm sorry.
Don't worry. Is there any setting button that you can fiddle with? Because it says host disabled attendee screen sharing. So I think Sam is suggesting that there is.
All right. So let me try to maybe make you. All right. I'm sorry, that was absolutely unexpected, because last time we didn't have problems. No, okay, that was not the best. All right. Now it doesn't work yet. Yeah, I'll make Chiara a host. Okay. Yep. I'm sorry, you have your mic off.
Great.
Sorry.
Okay. This is shared. I'm gonna now go into the presentation mode and collapse this. Okay, can everyone see me and also, see the screen and hear me fine? Shall I just go ahead?
I can, and yeah, we'll wait for answers in the chat. Maybe.
Okay, just let me know when I can go, and then.
Yep, all right.
Great. Okay, so having solved this unpredictable event, problem, whatever, we can, so I can briefly start introducing the topic. So I think the reason why I chose this topic is because I have worked a lot on both the idea of locality as a principle of physics. So I thought during my research about this, the issue of whether, our universal and fundamental descriptions of reality are actually local. And also because recently I entered a sort of long discussion with other people who are interested in quantum field theory about the Aharonov-Bohm effect, which, as some of you may know, is supposed to be one of the cases where the non-locality of quantum theory pops up most dramatically. And I think I'll just go through a little bit of an introduction about locality, and then I'll zoom in into this topic of the AB effect. So the first thing I would like to clarify is what I mean by locality, because of course there are different notions of locality, and I think in quantum theory you encounter at least two or more. So when I talk about locality, I refer to this thing that's called sometimes the principle of local realism, which means that when you have a composite system like this one represented here, indicated by this arrow, where you have two subsystems A and B, you'd like to be able to have a realistic description of this system where you can describe the full factual situation of A with a descriptor little a, and the full factual situation of B with a descriptor little b. This is realism. And also locality is the fact that if you apply a transformation that only involves A, let's say, only little a can change, but b cannot. So the fact that if you do something over the A region, the other regions in the universe are not affected. And they're not affected in an absolute term, not just as far as their observable features are concerned. Because if we go into this one, we are talking about a weaker property, which is not local realism, but it's the no signaling principle. The no signaling principle is something that has to do with the stuff that can be observed. So if you do a transformation on A only, let's say, the theory is no signaling if the observable feature of B don't change as a result. But something else which you can't observe, let's say, just by looking at B may change. Now, the reason why I made the distinction between these two things is that quantum theory is a theory that satisfies no signaling, but sometimes is said not to satisfy local realism. And this is the thing I want to discuss in the next slide. So if you consider the no signaling property, of course, quantum theory is no signaling. We're all happy about this because if you look at, if you describe your quantum system A with its local reduced density operator, rho A, and the system B with its reduced density operator, rho B, then because of this nice short proof that is in this line over here, if you have a joint state rho AB and you do a unitary transformation or a CP map, if you like, that only involves A, because of the properties of unitarity or of CP maps in general, you can say that the local descriptor, that the local density operator that describes B only is unchanged. So quantum theory satisfied no signaling, and we're all happy about it. However, there is this residual problem that if you take the tensor product or the ordered pair rho A, rho B of the reduced density operators, you don't get a description that is complete for the full system, because sometimes you could have an entangled state which cannot be described as like, let's say, a tensor product of these two density operators. So hence the question, does quantum theory satisfy also local realism? And I think the consensus, well, there has been a tradition within even quantum information, and actually this dates back, of course, to Einstein and to the founding fathers of quantum theory, that says that actually quantum theory is not local realistic. And the chief example, of course, is of something non-local, is the case of, let's say, two entangled particles. So you got like a state like this one where A and B are entangled. And now if you apply a transformation like this Z operator, I'm thinking of this as qubits, and you flip the value of the bit of the qubit A, well, what happens is that the full state changes. So you can't say that only the state, the state describing A has changed. And you can't really ascribe the descriptor that fully describes the state of A and the state of B, because this is an entangled state. And so even if entangled systems completely satisfy no signaling, there is still this problem that they present, whereby if you apply a local transformation on one of the subsystems that's entangled, it looks like you're changing the global state of both systems. So it seems to clash with the idea of locality or realism. And I mean, of course, this is an old idea. So I think this was made popular by I mean, it was pointed out at first, I think, by Einstein, Podolsky, and Rosen in a paper. You know, if you go on Wikipedia and you look at what quantum non-locality is supposed to mean, it's the phenomenon by which the measurement statistics of some states of a multipartite quantum system don't admit an interpretation in terms of local realistic theory. And if you take Einstein, Podolsky, Rosen's view, as well as the view of lots of quantum theory people, this is actually true. So quantum theory satisfies no signaling, but it doesn't admit a local realistic model. And why do we care, you could say? I mean, no signaling, after all, is all about observable features, and that's all we care about in physics, isn't it? And I think it's not, because, as I said here, the other universal theory that we have, which is GR, is actually a theory that is local realistic. And if you had quantum theories being a non-local realistic theory, then you would have this problem of reconciling these two theories. And it would look like a reconciliation is almost impossible. So in a way, this is like a blow to the view that you can actually have a consistent way of putting the two theories together. So it's important actually to understand if quantum theory can, after all, admit a local and realistic description, formulation. So my thesis, the controversial stuff that I want to say, which is, I think, not so controversial in certain circles, is that if you take quantum theory seriously, I'll say what I mean by that, non-locality actually disappears. So this idea that quantum theory is not a local realistic theory is just not true. And there is a price to pay for that, and I'll explain what that is in a moment. So what do I mean by taking quantum theory seriously? So the first point is that you switch to a view where your elements of reality are not real value stochastic variables. So they are not the real value stochastic variables that describe your measurement outcomes. But your elements of reality are Q numbers. So they are quantum numbers, not C numbers. And so they are more exotic than, let's say, what you would use in classical physics. And the other point, of course, is that unitary quantum theory applies to everything in the universe, or I should say in the multiverse, including observers, even macroscopic ones. Of course, there is decoherence, and we don't see quantum effects at certain scales. In most cases, but quantum theory does not have inconsistencies when it's applied to such objects, and therefore, to understand where it's local and realistic, you have to really take it at face value and consider it in its full power, even as applicable to these systems. And I think quantum information actually naturally leads to both points, especially to point 2. Because it's customary in quantum information to regard a measurement process as just another unitary, which you can think of as a controlled gate, so a controlled knot or a generalized controlled knot. Now, to see why quantum theory is local realistic, you have to switch to the Heisenberg picture. And so this picture is extremely unpopular among, I think, quantum info people. Other than, some few people who use it a lot. One of them is Daniel Gottesman, who pioneered it in its his way of expressing error correcting codes. And also it's been revisited by Deutsch and Haydn more recently in relation to locality. So the stuff I'm going to say now is something that was pointed out by Deutsch and Haydn, but I think it's also implicit in the traditional quantum field theory, because even though the Heisenberg picture is not very popular in quantum information, because it's very cumbersome in a way, it is very popular for quantum field theorists. And it's got some benefits. It's not great for calculations. The Schrödinger picture is more immediate, but it's nice because it shows explicitly in what sense quantum theory is local realistic. So to see that, you just have to go back to considering a composite system of two qubits or two systems. So A is now a qubit and B is another qubit, and you're considering two qubits. And you describe this composite system as specified completely by sets of descriptors that you can identify with the generators of the algebra of observables of A and B separately. So you will have, let's say, a triplet for qubits of operators that describe A, and another triplet that describes B. And these are, so QAX, QAY, QAZ. Each of these can be represented with a 4x4 matrix, which can be written like this, for example, with the Pauli matrices. And importantly, you have that QA and QB commute because they represent separate systems. So I think that's one assumption that that is taken to indicate the fact that A and B are two separate subsystems. Now, if you go by this way of describing A and B, you can see that the dynamical evolution is given by some unitary which acts on the full system and evolves separately the descriptors of A and the descriptors of B. And then in order to extract the observable things out of these Q numbers, you use a fixed constant of motion, which is the Heisenberg state, which is the initial state of the system, which you fix at the start. The observable features, let's say time t, can always be written as a function of these constants. So you can write it like what I did here. Now, the interesting fact that comes out of unitarity is that you can actually track the evolution of the product of the descriptors at one time by looking at how each of the two descriptors for A and B separately evolve. So there is this nice separability feature which comes out of this of the Heisenberg picture, which doesn't exist in the case of the Schrödinger picture. And note that this is true even in the case where you have entangled systems. And this is why in this picture is so nice and clean to see that that actually quantum theory is local and realistic. And this is what I think Deutsch and Haydn pointed out nicely in their paper. So let's go back to our criterion for local realism. You want to know how do transformations that act on, let's say, A only affect the descriptors of B. And the theory is local realistic if descriptors of B are not changed. And of course they are not changed, because the definition for a unitary to act only on A is that it's a function of the descriptors of A only. And so when you look at what it does to the descriptors of B, because they commute, it doesn't do anything to them. So you have it like this in one line, that actually quantum theory does satisfy local realistic criterion, assuming that the descriptors of the subsystems are Q numbers. And this is, again, true even when A and B are entangled, and you can generalize this proof also not for unitaries, but for CP maps. So it's very general. And it's quite nice. And I think quantum field theorists have known this all along. It's just that somehow the terminology of non-locality, which is very popular in quantum info community, has been developed by somewhat disregarding this fact. And it's very misleading if you think about it. So let me just kind of clarify something, because probably someone is worried about Bell's theorem and the fact that, how does this claim that I just made, that quantum theory is after all local realistic with the descriptors being Q numbers, square with the fact that we know about Bell non-locality. And this is why I'm saying that the terminology is misleading. So I've just to remind you, I reported here a bit of an example of a Bell-like inequality where you have an observable here, which is like a witness of entanglement. And if the expected value of this observable exceeds a certain number, in this case it's 2, then Bell's theorem says that whatever composite system you're describing cannot be described by a local real valued stochastic theory. And this has been taken as meaning that actually quantum theory is not local realistic, but this is not quite right. So the reason why it is not quite right is that this conclusion disregards the fact that you can still have local realism, just you have to drop this idea that the local descriptors are real valued things. And I've reported here this nice Nielsen and Chuang excerpt where the conclusion from Bell's inequality is that the world is not local realistic, and And somehow what I'm saying is that this statement has to be understood as meaning that what Bell's theorem rules out is just local real-valued models of quantum theory. But there are local and realistic models which have quantum numbers as descriptors. And this is obvious in the Heisenberg picture. And so whenever you violate Bell inequalities in the lab, you are just reinstating the fact that quantum theory is quantum theory and that the local descriptors of your systems are actually Q-valued numbers. So this is actually quite nice. It's quite nice because it's a bit like the idea of any kind of new and groundbreaking theory. So such theories make us think in ways that are very counterintuitive, because it's very hard to imagine of Q numbers descriptors for your local systems. But once you do, then you have this nice payoff that your theory is local and realistic and everything. Now, there are, let's say, two, I would say, residual non-localities in the literature. So if you buy this stuff that I just told you, so if you kind of buy into the idea of thinking of your the atoms that compose yourself as also being described by Q-numbered valued things, which are local and realistic, etc. Then you still have two problems. So there are still two things that are considered as having non-locality, which is not of the type that I just described now, at least on the surface. One kind is the one that appears in the Aharonov-Bohm effect. The other one is the one that appears in fermionic quantum field theory, because the descriptors that you use in that theory pertaining to different subsystems don't commute. And this violates one of the assumptions that I had in the earlier slides. And I think there's a lot to say about this, but I will now focus on the Aharonov-Bohm effect mainly. I'll go back to fermions in the conclusions. So let me explain the context of the AB effect. So the AB effect tries to falsify the idea that all quantum phases are acquired locally. Locally means this in this context. So you have here a Mach-Zehnder interferometer, and there's some kind of charged particle, for example, that's going superposed across these two paths. And suppose there are different values of a field at x1 and x0. This will generate a relative phase between the two branches, which is detectable upon closing the loop. Now, of course, you can use quantum field theory to also tell you that actually the phase is not just detectable upon closing the loop, but in principle, you can detect it by doing local tomography on the particle at any point along the two paths. So the phase is actually locally and gradually acquired along these two paths. And you can prove this by putting some shifters and various other things that you can do, for example, with photons, but you can do analogous things with charged particles and other particles, depending on what kind of experiment you're performing. Now, the AB effect is supposed to be an exception to this rule. And this is why it was supposed to be a proof of non-locality in a different sense from what I said earlier. So in the AB effect, you have, I'll just remind you briefly, you have like a solenoid, which is located at one point. It's an ideal solenoid, so it's kind of sticking out of the page. A particle, let's say an electron, which is charged, is split in an interferometer so as to go in two branches around this solenoid, and then the interferometer is closed. And what happens is that despite the fact that there's no field at the point where the electron is moving, you do detect a phase shift at the end of the, when you close the interferometer. And this phase shift is proportional to the flux of the magnetic field through this section. Now, why is this problematic? Because as Aharonov-Bohm pointed out, the there's no Lorentz force, as it were, on the electron or the charged particle when it's kind of traveling along this path. And so it looks like the action of the solenoid is felt at a distance by the electron. So that is quite weird. If you don't want to use action at a distance, you can also use a different model, which, let's say, resorts to the vector potential, which is this A, which is related to the B field with the curl. But the point is that in field theory, the vector potential isn't an observable quantity by itself. The observable things are the fields. And so it looks like, although you can actually formally write the phase difference along the path, this would be a function of A. And the standard argument goes that this is a gauge-dependent quantity and can be observed. So it kind of looks like this phase is popping up magically at the end of the interferometer, even though along the path there was nothing there. And this is, of course, not a local thing. It kind of clashes with the accounts that we have for all other phases. Now, to challenge it, I mean, this is a very interesting bit of history, by the way, because Aharonov and Bohm produced this paper in 1959, and they kind of used it as a way of saying how significant the vector potential is actually in electromagnetism. And to this day, there is a huge controversy as to what the whole effect actually means and how to model it. And like a huge number of papers have been written about it, but I want to focus on those that are worried about the locality issue. And one breakthrough happened in 2012 when Weidmann, who had been interested in this issue for a long time, came up with an interesting model to explain the phase. And this model is a model where the phase is actually due to the interaction of, not of the vector potential of the solenoid on the electron at the point of the electron, but it's due to the field of the electron at the point of the solenoid. So he writes down, let's say, an interaction which is involves the magnetic field generated by the electron and the magnetic field of the solenoid at the point of the solenoid, because elsewhere it's zero. And he shows that by appropriate integration of this formula, you can actually get the right phase when you close the loop. So this is kind of nice. So the phase is actually, in this interpretation, is somewhat proportional to the interaction energy that you can write describing the interaction between the solenoid and the electron at the point of the solenoid. And what is interesting, and this was pointed out by another physicist called Kang, is that in this interpretation, this model, the phase is actually well-defined, unlike in the other model, which uses the vector potential. It's well-defined along the path of the electron and for each point. So there is a nice well-defined value for each of the points of the path that the electron is following. So the idea is that this sounds like almost like a refutation of the non-locality of the AB phase, except that there is a problem. So the problem is this, that in the semi-classical model that Weidmann has, the interaction between the field of the electron and the field of the solenoid happens at the solenoid point. Why? Because there isn't classically any field at the electron's point. That's actually the problem that we had at the start. So the way he describes this is that the phase is somewhat gradually constructed, but it's not clear where it is along the path, whether it's actually available on the electron or whether it's somewhat non-locally shared between the electron and the solenoid. Of course, it must be on the electron, but the model that Weidmann uses cannot describe this because, and I go back to this idea of taking quantum theory seriously, because it's not a fully quantum model. In order to see that the electron really carries the phase along the path and that the phase is gradually acquired, and if you were to measure the electron, let's say at this point, you'd be able to extract this relative phase. you have to model the whole thing quantum mechanically, which means that you have to quantize the field as well. And so I think this is what Vlatko and I have been doing. So I won't bore you with the details, but basically the gist of the explanation is that you can write a nice second quantized Hamiltonian for the electron, the solenoid, and the photon field, which connects, as it were, the solenoid and the electron. And because now your elements of reality are the Q numbers of the field, even though classically there's no field at the point where the electron is, there are Q-valued entities that can mediate the interaction between the solenoid and the electron. And so in this account, with the full quantum model, everything is local. And most importantly, you can actually, and this is the first point in this slide, you can actually measure, in principle, the relative phase between the two branches of the electron at each point along the path. And this is very cool because this suggests a possible way of performing a new experiment along the lines of local tomography, let's say, where you can extract the partial AB phase. And if you were to do that, you would be able to vindicate this idea that the AB phase is actually locally acquired. So this is very exciting. And I think somehow, well, it's exciting because although it proves something that to, let's say, quantum field theorists might look self-evident, because I think no doubt they think that all of the descriptions they have must be local, it would somehow clarify this mess about non-locality that has been introduced by some interpretations of the AB effect. Having said that, in the quantum description, the vector potential is very important because we can't write the Hamiltonian without a quantized vector potential. So the original point of Aharonov-Bohm still stands, and it's actually made it even more significant once you look into the quantum version of the model to explain everything locally. Okay, let me just make a separate statement about fermions. I promised I would go back to this. And I think I have, because I'm collaborating with Niceto, who is kind of very keen on fermions. So I think I'm not sure if he's here, but just in case. So there is an interesting theorem that was published. It was kind of published in 2017 by Gilles-Brassard and Paul-Raymond Robichaud, which says something very intriguing. And this is that all theories that are that have a deterministic dynamics, and namely a unitary one-to-one dynamics, and that satisfy no signaling, like quantum theory, must also have a model which is local realistic in the sense that I said. So a translation of this formal statement is that basically all unitary quantum theories that have a no signaling Schrödinger picture must also have a local realistic Q-valued expression using something like the Heisenberg picture version of them. So the conjecture here is that this residual problem with non-locality that happens with fermions can be solved in principle, because that's what the theorem says, because the fermionic quantum field theory is no signaling, of course, and it's one-to-one, so it's got a kind of deterministic dynamics. And so it must admit a model which is local realistic and uses Q numbers. It's just that the Q numbers are not the ones that we're using currently, so they're not necessarily expressed in terms of annihilation and creation operators. And I think this is some nice work in progress that I'm doing with Niceto, and so, you know, kind of watch this space. So hopefully this will be solved soon. So the conclusions are that quantum non-locality is a myth, in a sense, and this is clear if you take quantum theory seriously. And I think those who use the terminology of Bell non-locality or quantum non-locality are referring to the fact that you cannot describe quantum theory with a local hidden variable model, so with local real value stochastic theories, which is fine, everyone agrees with that, but it's a bit misleading at best. And those who actually think that quantum theory is non-local, well, they must be wrong, because as we've seen, that is not true. The second point is that because quantum theory, which is a universal theory of reality, satisfies locality in this sense, we can take locality as a fundamental principle to construct future theories of physics that go beyond quantum theory. So it's a good kind of guideline. And also under this, at least as far as locality is concerned, GR and quantum theory are not in contradiction. So that's kind of reassuring. So like going back to the theme of the talk, which is taking quantum theory seriously, I think I've experienced myself the benefits of this kind of take on things. So the thing is to switch to a view where Q numbers are the elements of the local elements of reality, as opposed to real valued outcomes of measurements. And the second point is to accept that quantum theory applies to everything in the universe unitarily, including observers and macroscopic objects, et cetera, et cetera. And if you adopt this view, you got a lot of benefits. So I've listed some of them here. It's like, you know, taking some kind of nice medicine that makes you feel better. So the first thing is that you will observe is that you will stop obsessing about things like the measurement problem and about quantum non-locality. Hopefully I've argued about non-locality now, and I'm happy to discuss the stuff about the measurement problem later. You might actually end up trying to do crazy things, but the crazy things that actually advance the science a lot. So you will stop doing experiments about just Bell inequalities, which now we have violated really well. So we are sure that they are violated, at least, you know, not sure, but I mean, we've had a number of such violations, and I think it would be nice to do something new. So for example, you could end up trying to superpose large masses and large biological systems, such as bacteria. Some colleagues of mine have done that. Cats and maybe even humans. I think David Deutsch has a nice thought experiment along these lines, and maybe at some point we'll be able to do that. And finally, you will just see that classical and quantum computing are not completely separate, but actually they're just two faces of the same local information theoretic structure that pervades the universe. And it will also support, it will be the same information theoretic structure that will support the new theory of physics that will supersede both quantum theory and GR. And so as a last thought, of course, I mean, one of the objections is something like, but I don't see Q numbers, so I don't feel like I'm in a superposition. So why should I actually embrace this view of the universe? And I want to reply to this objection, which is a really, really nice quote by Frank Tipler, which is this, and I'll read it for you. Have you ever seen Earth rotate on its axis? I have. I see it every day. When I see the Earth's rotation expose the unmoving sun at dawn and cover the unmoving sun from my view at dusk. Common language, however, says that the sun sets and rises. Everyone believed that this was so until Copernicus and Galileo taught us to see nature through the laws of physics. It is time to see that measurements of the electron spin frequencies through the laws of quantum mechanics, which apply not only to electrons, but also to the physicists who measure these spins. And with this, I'll close the presentation. I'm very happy to take questions, and I thank you for your attention.
Thank you very much, Chiara, for the talk. It was like mind exploding, mind broadening, or whatever you call this. So if you have any questions, please write them to the sessions of questions and answers, and maybe to chat. I think Chiara will be happy to answer them. But by the way, I have a question already.
Yes, great.
So what are these, like I understand all these nice concept of Q numbers that they make the theory local, but like, what are they? How can I kind of not measure? I don't want to say measure, but how I can measure them? How can?
Yes, I think so. I think it's hard to say what they are like, because as soon as you ask that question, then you're thinking, how can I actually picture them in my head? I guess the answer has to be along the same lines as you would do for, let's say, space-time, right? When we think of relativity and the way it describes the fundamental things in the universe, and we think of a curved space-time and the way it works, etc. This is very distant from like the intuition that we have, but it still works. So they are objects which we can't completely access through measurement, but just like we can't really access completely through measurement the whole space-time, we can at best do some local measurements and infer something about the curvature and so on. And likewise, in this case, I think that the best way of understanding Q numbers is really to go in this idea of the multiverse. So, whatever de Wit and several other people, including David Deutsch and David Wallace and other physicists have described. But so in a way, you only have an imperfect description of these things because you can only describe them as far as, through the indirect observations that you make when you perform interference experiments. So we kind of catch glimpses of these things. We can let's say we can say that they are the best things that we can use at the moment to describe in a local way what's going on in a quantum interference experiment. Mm-hmm. And my understanding, and also I think there are some people who are working with David, for example, Sam, I think he's tuned in now, that so there is a lot of, there's a lot of work to do in order to have a complete nice picture of what the Q numbers really are. So I think your question is very nice because it kind of talks about a research project in a sense. But this is probably, my expectation is that this will be fully clarified when we have a new theory of quantum gravity. So we'll have to wait until then. But I think somehow I understand that your point is that these things are very exotic and maybe not so friendly to imagine. But I would say it seems to me that they are not less friendly than, they seem to be as unfriendly as let's say other things that GR uses to describe the universe. And yet with GR we are okay, but we're not quite okay with Q numbers. And I think this is partly because this has to do with information theoretic structure and so on. But it requires a bit of kind of imagination, but I think it kind of works out nicely. And if that's the price to pay for locality, I'm very happy to pay that.
So, yeah, so the question is, if it's valid to describe physical systems, like with the things you cannot measure. Well, I understand that like it leads to consistency in what we expect but yeah, we have another question from the chat. So Logan Chipkin asks, do you think the principle of locality will be shown to be deducible from even deeper principles, perhaps from those of constructor theory, or might a different theory be required? Okay, that's a really cool question. And hi, Logan, by the way. So I think so in constructor theory, locality is one of the things that we assume. So I think it's not going to be from principles of constructor theory. I think one way of thinking of locality, at least of locality of interactions, is that it kind of rests on a further assumption, which is the assumption that we can divide the universe into subsystems. I mean, if you don't have subsystems, then you don't even have, you can't formulate locality because there isn't such a thing as a local descriptor or something. So I think let's say this is not a principle that implies locality, but one of the assumptions or the more fundamental axioms that it rests on is the fact that we can subdivide the universe into subsystems. And I think this is a very important assumption for anything that you want to do in physics, whether experimental or theoretical. All right. We have another question from Anthony Thompson, our beautiful presenter from the Journal Club. And he asks, please, can you explain how using Q numbers lets us stop worrying about the measurement problem? Right. This requires a very long discussion that I'm happy to have offline. And also I think there are lots of, this has been discussed a lot by, the ultimate discussion of this in this book by David Wallace. So, I recommend it if you're interested in this kind of stuff. But basically, I think it's an indirect way, in the sense that I think the measurement thing measurement problem is really solved by the other bit of taking quantum theory seriously, which is just to treat any measurement interaction as a unitary transformation. So if you do that, then everything is consistent in the sense that you describe the thing that performs the observation as just another quantum system.
So in the same way as you can describe consistently a control knot between two qubits, you can describe a measurement interaction that takes place between, you know, myself and a photon, with me looking at the photon and checking where it is. And all of this carries through and is nicely and beautiful and consistent, and there is no contradiction or problem with the fact that you're performing measurements. And somehow this is nice because whenever you do that, you are so you get rid of this artificial division between macroscopic measurement systems and the stuff that's being measured, which is quantum. And somehow, time and again, in most of the stuff that I described today, even in the case of the AB effect, whenever you add this artificial distinction between something being classical in the AB effect is the field and something being strictly quantum, you may reach various kinds of contradictions or problems. Because whenever something that's quantum couples to something classical, it somewhat infects it with the quantumness. So if you start with the view that the stuff that's classical is classical and can't become quantum, you'll end up in some contradictions. And the measurement problem is just one of these.
Yeah. I have one more question. Federica Bertagna asks, I will, so like to all who are listening to us, I will read this question and then probably you can see it, but then you'll see it. Thank you for the nice talk. I don't understand how you can use different set of elements for theories that describe a same system. If you apply Q numbers to quantum theory, why don't use them to GR? By doing so, would GR be the same? Hope it makes sense. You can read it if you.
Yes, I think the problem is that so GR has a formal structure where the standard quantization procedures don't seem to work, and one of the reasons why that happens is that Einstein's equations are nonlinear. So that's one of the formal reasons why it's been said that it's hard to find the Q number description of the whole of GR. What you can do though is to do some approximations, and in those approximations you can indeed describe the gravitational field as made of gravitons, which are a bit like photons, and in that case you can think of all of these quantum numbers as being your descriptors, and everything is fine. However, it's not quantum gravity yet because it doesn't capture the whole of GR. And I think the tension there is, well, I don't think there's a conceptual tension. I think it seems to, to me, although I'm not an expert on this, of course, that the problem is that we have only been trying to apply to GR known quantization procedures or variants of those. But the fact that we haven't managed to find a way of doing it properly doesn't mean that there isn't one. So, I'm hoping that some of you maybe might come up with that. That would be very nice.
And another question. I'm sorry, I can't make everybody see this question, so I'll just read them. Nicholas Petropoulos asks, hi, I want to ask that, do you have an opinion about if the parallel worlds are physically real in many world interpretation, I guess? Thank you.
Yes, I think so this is the realm of interpretations of quantum mechanics, and of course, you can explain the patterns that we observe in the experiments in various ways, and there are even some collapse models that kind of move away even from the unitarity of quantum theory that can, let's say, explain more or less what we see. But if you stick to certain features like locality, this idea that quantum theory is universal, so it applies to everything and so on, then I think the many world description is almost inescapable, in the sense that it's just natural to interpret these Q numbers and the way they work, and they kind of evolve under unitary transformations as describing different branches of the wave function being transformed as they get entangled as a system gets entangled with another, and yet with another, and so on and so forth. So yeah, I think I would say that they are real, just like I think space-time is real to some degree. Although I mean, as you were saying earlier, you can't access the whole of space-time, or you can't access the whole of this multiverse. But yeah, I mean, I think this is the conclusion that this type of interpretation leads to. So yeah, I mean, my opinion is that the branches of the multiverse are out there, and I am in one of them.
Okay.
We are in one of them.
Yeah. Oh, Discord, we have one more question from Claire Christianson. Could you explain exactly a Q numbers is in this context, and how do they arise in quantum measurement? For example, in standard quantum mechanics, if you measure the z spin of an electron, you get either real numbers 1 or -1, the eigenvalues corresponding to eigenvectors of the observable. How would the Q number arise here?
So the Q number is what is needed to describe the. So you can write down in the Heisenberg picture the interaction that leads to a measurement is. So first of all, we have to assume it as a you have to kind of accept the fact that this is a unitary transformation.
I don't mind.
Right. So it's going to be so you got something that's being measured, so system A, and then there's another system B that's kind of the thing that measures system A. And you can write it as a controlled operation, let's say. If there's a qubits, you can think of a control knot, so that, because quantum information society, so let's go with qubits. So that interaction can be described in the Schrödinger picture as a copy-like transformation. So you got 0, 0 goes into 0, 0, and 1, 0 goes into 1, 1, and all the others things in the basis. But you can also write it in the Heisenberg picture. And in that picture, the unitary that performs the control knot will transform the descriptors of your subsystems. And so you start with QA and QB, which are your descriptors of qubit A and qubit B. And then you apply this control knot. And what you see, and this is interesting because you see it only in the Heisenberg picture, is that the descriptors of the two qubits at a later time are a function of the descriptors of the qubits at an earlier time. And the descriptors of the two subsystems have mixed. Mm-hmm. And so this is the signature of the fact that a measurement has occurred or an entangling operation has occurred. And the way they have been mixed, and you can check it by doing the calculation, is that the descriptors of qubit A at a later time, so after the C naught has been applied, don't commute with the descriptors of qubit B at the earlier time. Mm-hmm. Mm-hmm. Initially, they did commute because we said that separate subsystems have to commute. But if you apply the control knot, then this guy, qubit A, will contain in its descriptors the elements of reality, as it were, of qubit B, and vice versa. So the measurement is nicely described in the form of mixing the descriptors of qubit A and qubit B, and in the descriptors of the two qubits at a later time. And this is nice because it shows how, let's say, information flows from one system being measured to the other system measuring it. And it's completely symmetrical. So I think the fact that you describe your system's Q numbers is completely compatible with the fact that you have measurement occurring. It's just that you can't describe the measurement as being, given by various outcomes. So to describe the outcomes, you have to use the Schrödinger picture. Mm-hmm. But that's fine because the two pictures are consistent. So. Mm-hmm. Should I look at the? Yeah.
Yeah. So I don't know if you have any other questions. But it looks like that we don't have any. I have a question. Like, so, where at what point, like in your life, you start believing in many world interpretations? For example, did you?
I think. Well, I think it happened naturally as I was understanding quantum theory better. So I was horribly confused at the end of my undergraduate degree, in the sense that I think most of the stuff that I was told was in the form of collapse theory. So, you know, the idea that if you measure one qubit and it's entangled with something else, it collapses in one of the states that are kind of connected with the outcome that you've just observed. And I mean, I really forced myself into believing that, because I thought, the lecturer is saying that sounds right, but it didn't quite make sense, because when you go in, so of course you can try to make sense of it somehow in a contrived way, a bit like when you're trying to fit think that the Earth is the center of the universe and not the sun, right? So it's kind of that kind of theory that you can still make it work more or less, but somehow it's very unnatural. And so gradually later, and when I started doing quantum computing, you use all of these unitary gates. And I think as soon as you do that, then you really are already thinking many worlds, although maybe not explicitly. So maybe you are in denial of many worlds at that point. And I think later on, it just kind of became I don't think it's a completely unsatisfactory interpretation of quantum theory. It's got problems, but it seems to me that the problems it has are far fewer and far less dramatic than what the other interpretations have. So I think it's like I'd like to understand it better, but I guess this is the best way of understanding quantum theory right now. So that's how I kind of ended up thinking about it like that.
Well, so once we have talked about the many world theory, we get more questions. Yeah, I need you, Thibaut, that ask us, would you say that Q numbers are the same level of awareness that quantum states, but ones are the non-commuting operators represented by matrices, and the others are Hilbert space elements represented by vectors for pure states? So, I'm sorry, I didn't get the question in this time, but yeah.
Yes, I guess so. Well, I mean, maybe one comment I can make, which is along these lines, is that I think it's perceptive to mention Hilbert spaces, because one thing that might interest someone, depending on what kind of angle you are looking from, is the fact that the Heisenberg picture and the Schrödinger picture are kind of equivalent as far as measurements are concerned, of course, because the predictive statistics are the same. But we already seen that in terms of locality, they are a bit different. So in the sense that one is more explicitly local than the other. And the other difference is that, going back to the question, is that in the Heisenberg picture, you don't have to choose a representation. So you can forget about Hilbert spaces and just look at the operators as being your, the algebra of the operators as being the main thing. In addition to this map, which you have between this space of operators and the C numbers, which is given by the trace, and the Heisenberg state, which is your constant. And this is useful because sometimes there are cases where finding representations is problematic. So I think there's a paper that actually Vlatko found and kind of sent to me, because he knows that I like Heisenberg, where Dirac, apparently it's one of the last papers that this guy, that Dirac wrote. It's called kind of quantum field theory without deadwoods. And Dirac is trying to say that certain representation problems which happen in quantum field theory, to which he refers as deadwoods, disappear if you switch to the Heisenberg picture. And the reason, although I don't understand the paper fully, I think the reason is that in the Heisenberg picture, he points out that in the Heisenberg picture, you can do without a representation without using Hilbert spaces. And you can just use C-star algebras, really. So it's a kind of nice asymmetry. And maybe the question was kind of hinting at that.
Mm-hmm. Okay, all right. One more question from Nicholas Petropoulos. Have you heard of causal set theory? If I'm not mistaken, isn't there the point that locality and causality emerge at a higher level of some sets of points connected with some rules that impose causality and locality? If that's true, how can we assume locality is fundamental? Thanks again.
Right. So I don't know about that, but I think so. It could be that there is that there is a way of deriving locality from something else. So I'm actually very happy if there is an axiom that, a physical principle from which you can derive the locality principle. I mean, usually when you find that something that's physically meaningful can be used to derive something else, you are maybe explaining this something else better. So in a way, this would provide a better explanation for what locality is. Although, because I'm not familiar with what, with that, I mean, it sounds to me it's more mathematically inspired rather than physically inspired. But maybe it's the scope to understand whether these axioms that they're using can be interpreted physically in some way. So it sounds cool.
Yep. So maybe I think we would stop at this point, because maybe Chiara has answered already too many questions. Thank you very much for the talk. For me, it was a great pleasure, and I did learn a lot of new things.
Well, yeah, thank you for inviting me. I really enjoyed it.
Thank you for agreeing to give a talk.
As I said, I'm really pleased with it sounds like you're doing really well. The society is very lively, and it's a pleasure to see that. It's really cool.
Great.
Yeah.
Yeah, thank you very much. So thanks for the amazing talk. Nicholas Petropoulos says that guy was asked 2 questions. Thank you, Nicholas, for your question. So to everybody who is still here, I know join our Facebook page, follow Chiara Marletto's research. I don't know, enjoy your life and enjoy your Saturday evening. Thank you, everybody.
Have fun. Bye. Bye, guys. Bye.
I think you should stop the webinar, because now.
Shall I close it?
Yeah, you can just have a nice day. People
Same
saying they so
take care.